Our next task in developing our theory of geometry is to develop a way of measuring angles, that is, of associating some sort of number to an angle to tell when angles are bigger or smaller or the same size. This is similar to what we did with distance, and we use distance to define congruence of segments. With angle measure, we're going to introduce a new function that associates to every angle a real number. Now, the specific scale that we use for angles is arbitrary. We could use the radian measure from trigonometry, we could use familiar degree measure, or we could use something else entirely. For familiarity, we're going to use degree measure here, but I wish to emphasize that this is a completely arbitrary decision. Basically, you can decide to let a right angle be any measure that you like, be associated to any real number, and the rest of the theory would fall out. The specific numbers that we use for angle measure are really not too relevant, so we will arbitrarily choose to use degrees simply because they're familiar. So let's start with our definition. Definition 33. An angular measure on a geometry is a function which we will denote using a lowercase m, and it's going to go from the set A of all angles to the real numbers. So where this fancy A is the set of all angles in the geometry. And this function has to satisfy 5 axioms. Axioms A1 through A5. A for angle measure. So just like with distance, we have a certain collection of axioms that we want our angular measure to satisfy. There are 5 of them. There are a few things that we need to lock down about how our angle measure is supposed to work. So axiom M1 is sort of a restatement of some of the things that we've said so far. That M is a function from A to R, and when angle ABC is an angle in our geometry, then we write just measure of angle ABC for measure of angle ABC. So we'll drop the parentheses from the function notation typically when we write down the measure of an angle. As always, make sure to keep track of the difference between the angle and the measure of the angle. If we write down just angle ABC, that's an angle, it's a set of points in our geometry. Whereas the measure of angle ABC is a real number and therefore behaves like a real number. This is very similar to the distinction between a segment and the length of that segment, or the distance between the two endpoints. Axiom M2 tells us what sort of numbers we can get out of this. So for any angle ABC in the set of all angles, the measure of angle ABC is a real number that is positive and is strictly less than 180. So we're taking our normal degree measure here. Also, our angles are always going to be measured basically in the shortest way possible. So if I look at this angle here, in trigonometry, I could describe this angle in a number of different ways. I could describe it going around this way, counterclockwise, coming around the other way, or even going all the way around once, and coming back here. So in trigonometry, we talk about angles of all sorts of degree measures, positive, negative, 0, etc. We're not doing that. Essentially, when we look at an angle, the angle measure is going to be the smallest way of getting from one ray of the angle to the other, rotating around, and also we don't associate any direction to it. So all angles are between 0 and 180 degrees, strictly between 0 and 180 degrees, because remember, we do not consider a line, that is two rays going in exactly opposite directions, to be an angle. So that's our axiom M2. Our axiom M3 is, we'll call it the angle construction postulate, which says that given a ray AB on the edge of a half plane H, and given an R, some number R in the interval 0 to 180, there exists a unique ray AC with C in H and the measure of angle BAC being R. So this is telling us that if we have some ray AB here, and it sits on the edge of a half plane. Now, this ray actually sits on the edge of many half planes because there are lots of planes containing this line AB, but if we specify one of them, if we say, oh, we're looking at the half plane above this line here, and I give you any angle measure between 0 and 180, this axiom says that there does exist an angle with that measure where the other ray of the angle lies over here in H. So if R is small, we'll get a small angle like this. If R is big, we'll get a big angle like this. But the point is that every possible R appears as the measure of some angle. And that angle is unique. So if I have two angles that I somehow know both extend off into the half plane H and have angle measure R, I know that those two rays have to be the same. Excuse me. So this tells us that we can construct angles how we like, or with any measure that we've got. Axiom M4 is angle addition. And it says that if D is in the interior of angle ABC, then the measure of angle ABC is equal to the measure of angle ABD plus the measure of angle DBC. So let's look at the picture of how this goes. Let's say I've got my angle ABC over here. And then I've got some point D that lies in the interior of that angle. So it's going to be somewhere there. So then we can look at the angles ABD and DBC. And what this axiom is telling us is that the measure of angles is additive in the intuitive way. If I take the red angle plus the yellow angle, that is angle ABD plus angle DBC, then that's going to give me the measure of the green angle, which is the angle ABC. And again, this is quite intuitive to us, and our intuition does serve us quite well when it comes to how the arithmetic of angles interacts with each other. There's quite the analogy between the arithmetic of angles and the arithmetic of segments. And in fact, it's possible one could construct a very high-level theory creating a sort of analogy between them that would allow you to translate proofs and so forth, but that's something that we're not going to be approaching here. Now, before we get to the last axiom, it's useful for us to introduce a new definition, a new piece of notation, or definition. So definition 34 has to do with the following situation. So let's suppose that I do have two rays that sit like this, and I've got I'm sorry, I'm getting slightly ahead of myself. Definition 34, we want to define what it means for two angles to be congruent. We defined two segments to be congruent when their lengths were the same. That is, when the number that we associate to that segment is equal. We can do the same thing here. So definition 34 says that two angles, angle ABC and angle DEF, are called congruent, and we write that angle ABC is congruent to angle DEF if the measure of angle ABC is equal to the measure of angle DEF. So this is very similar to how we define congruence of segments. We basically co-opted equality of real numbers to define congruence of angles. And you can use this to prove that congruence of angles is an equivalence relation, it's reflexive, it's symmetric, it's transitive, using the fact that equality of numbers is reflexive, symmetric, and transitive. So this is just how we're going to define congruence of angles. And there we have it. And then continuing the definition, if B is between A and C, that is, we're looking at the following type of situation. We've got a line, and we've got points A, B, and C on it. Well, then we don't consider this to be an angle, because remember, for an angle we needed two rays that were not collinear, that didn't lie on the same line. However, from trigonometry, we know that we would want the measure of a straight angle to be 180. And so it's going to be useful for us to talk about this. And the way we're going to do that is by defining supplementary angles. So if ABC and D is a point that's not in the line AB, then angle ABD and angle DBC are said to form a linear pair. Or we would say that they are supplementary. If, in addition, we have that angle ABD is congruent to angle DBC, then angle ABD and angle DBC are called right angles. So the angles ABD rather, and DBC form a linear pair in our sketch here, and therefore we would also say that the two angles are supplementary. If they were congruent to each other, we would say that they were right angles, and we would denote them with a little square instead of this curve at the base of the angle. Now that we have this definition, or the definitions of supplementary angles, we can now finish listing our axioms. Axiom A5 for angle measure says that if angle ABC and angle DEF form a linear pair, then the measure of angle ABC plus the measure of angle DEF equals 180. So we're not saying that any individual angle has a measure of 180, but if two angles form a linear pair, that is, they basically combine together to give a straight line, then the sum of their measures has to be 180. And this 180 here is the completely arbitrary point. We could have picked any positive number here in order to make the theory work. And if we do that, we would have to change one of the previous axioms where we specified that angle measure is always less than 180. But we could put pi here if we wanted to use radian measure, 180 if we want to use degree measure, 50 if we wanted essentially 100 to be the measure of a full rotation around the circle, and so forth and so on. This choice is totally arbitrary. But once we have it, it's fixed, and now we can use it to go forward. One of the most useful facts that we're going to have is that a right angle has a measure of 90 degrees, or of 90. Where for us, angle measure is just an arbitrary number, and we will also want to know that any 90 angle, any measure with angle 90, any angle with measure 90, sorry, is a right angle. We are so used to this fact that it may be a little difficult to really think about, all right, well, what actually needs to be proved here, but we have to be careful that we look at what we're using. We have defined right angles to be an angle that forms a linear pair with another angle that it's congruent to. So this is what we have to work with. So let's see how we use all these definitions for Theorem 35. An angle ABC, is a right angle if and only if the measure of angle ABC is equal to 90. Now, in particular, this means that all right angles are congruent, and any angle congruent to a right angle is a right angle. Now, the second sentence here is an immediate consequence of the first. Once we know that all right angles have measure 90 and any angle with measure 90 is a right angle, the second sentence follows immediately because we have congruence of angles being based on equality of their measures. However, the situation is a little bit different if we're working in synthetic geometry. I mentioned this a couple of lectures ago. In synthetic geometry, you don't assume that you have real numbers. You don't work with real numbers. You just talk about relations between points and lines and angles and so forth arbitrarily. And in synthetic geometry, you have to take the second half of this theorem as an axiom about right angles. We don't have to do that because we have the real numbers, but it is important to think about how this works, how this would work if we didn't have the real numbers to rely upon. The proof is pretty straightforward. So let's suppose that angle ABC is a right angle. Now, what does this mean? Going back to the definition, this means that there exists an angle DEF such that angle ABC and angle DEF form a linear pair and angle ABC is congruent to angle DEF. Now, since angle ABC is congruent to angle DEF, this means that the measure of angle ABC is equal to the measure of angle DEF. This is just by definition. And then since these angles form a linear pair, we have that 180 equals the measure of angle ABC plus the measure of angle DEF. But we just wrote that the measure of angle DEF is the same as the measure of angle ABC. Now remember that the measure of angle ABC is just a number, so since we've got it added to itself, this gives us 2 times the measure of angle ABC. So we have that 180 equals 2 times the measure of angle ABC, and therefore that means that the measure of angle ABC is equal to 90. So that shows us that if the angle ABC is a right angle, then it has measure 90. But that's only 1/2 of the statement. We also now need to show that any angle with measure 90 is a right angle. So let's go to that. And let me do this on the next page so I'm not trying to cram it in. So now let's suppose that the measure of angle ABC is equal to 90. We want to show that the angle ABC is a right angle. This means we have to show that it forms a linear pair with some angle that it is congruent to. So the current situation is the following. We have our angle A, B, C, and I've drawn it as a right angle because that's what we know we're aiming towards. Now we have to construct some angle that forms a linear pair with this one. So the easiest way to do that would be to construct a ray going this way, say. And now once we do that, then we'll have that the angle ABC and the angle DBC form a linear pair, and that will at least get us part of the way there. Hopefully we'll be able to prove that those two angles are congruent to each other. So let's let D be a point in the line AB such that B is between D and A. So We're using our sketch over here on the right as a way of keeping track of our thought process, but we're not actually referring to it in the proof because a picture is never a proof. So now, angle ABC and angle DBC form a linear pair. So, by axiom A5, the measure of angle ABC plus the measure of angle DBC equals 180. Now, we assumed at the beginning of this step that the measure of angle ABC is equal to 90. And so if the measure of angle ABC is 90, we have that the measure of angle DBC is also equal to 90 because we could just subtract 90 from both sides of the equation above. Hence, this means that the measure of angle DBC is equal to the measure of angle ABC. So that means that the angle DBC is congruent to the angle ABC. Hence, we have that angle ABC is a right angle. We have to make sure as we prove this statement that we're always referring back to the definition of what a right angle is. The original definition of a right angle for us is an angle that is congruent to another angle it makes a linear pair with. Now, the theorem, Theorem 35 that we have now, means that we have an alternative description of what a right angle is. We now know that a right angle is exactly an angle with measure 90. But we didn't define it that way. We could have, and then we could have proven that right angles have the characteristics that we want, but we would still have had to prove this, a version of this theorem. So when you are going and working on a proof and using a definition, make sure that you are either using exactly the definition as originally stated, or if you're using an alternative description like this one, that you note what theorem you're using when using the alternative description of the type of object you're talking about. All right, so once we have a right angle, and we know that all right angles have measure 90, this allows us to give another definition. So definition 36. So an angle ABC is called acute if the measure of angle ABC is less than 90, and obtuse if the measure of angle ABC is greater than 90. So trying to define acute and obtuse without making reference to the fact that we know that all right angles have a measure of 90 is complex. It takes quite a bit of work. But once we know that all right angles have measure 90, that gives us an easy way of describing what acute and obtuse angles are. All right, so then we've got a couple of quick theorems. Theorem 37. Congruence of angles is an equivalence relation. That is, it's reflexive, symmetric, and transitive. I already mentioned that a little while ago. That basically just comes from the fact that equality of numbers is an equivalence relation. The proof of it is almost exactly the same as the proof for congruence of segments being an equivalence relation, so I'm not going to do any more with that. Theorem 38 is called the angle construction theorem. And it's very similar to the statement of axiom M3, which we called the angle construction postulate. The only difference here is that the axiom talked about construction of angles based on a particular angle measure, and Theorem 38 is going to talk about constructing an angle that's congruent to some known angle. So let's let angle ABC be an angle, and ray EF a ray on the edge of a half plane H. There exists a unique ray EG with I beg your pardon, let me restart that. There exists a unique angle DEF with D belonging to H such that angle DEF is congruent to angle ABC. So let's sketch out what the situation is here. We've got some angle that we're starting with and some ray. Let me give these labels. So we've got the angle ABC that we're starting with, and then we've got a ray EF, and then we need to specify the half plane that we're working with. Let's work with this half plane over here. And what this theorem is telling us is that there exists a unique angle DEF, where D sits in the half plane H, such that these two angles, the blue angle and the green angle, are congruent to one another. Now the proof for this is pretty straightforward. The angle ABC has some measure R. Then by the angle construction postulate, there's going to be a unique ray ED such that this angle DEF has the measure that we want. And that's pretty much all there is to it. Let's write out the proof really quickly. So by A3, the angle construction postulate, there is a unique ray ED with D in H such that the measure of angle DEF equals whatever we want, or any number between 0 and 180. So in particular, we're going to have it be the measure of angle ABC. But this means that angle DEF is congruent to angle ABC. And that's pretty much all there is to it. Now, one interesting thing you'll notice about the proof is that when I was sketching things out to understand how the argument of the proof was going to go, I identified this number R and used it in my sketch, but I didn't wind up using it in the theorem. That's okay. Sometimes you find more efficient ways of writing down your final proof than how you came up with it originally. That's good. That's what you want to happen. All right, so then we can combine two theorems together that we've worked with into one that's going to wind up being pretty efficient, pretty worth combining together. We have the angle construction theorem here, which says that we can get a unique angle that does what we want. And earlier we also had the segment construction theorem, which says that given a ray and a segment from somewhere else, you can always construct a segment on that ray which is congruent to the segment that you started with. We're going to combine those together into theorem 39, which I call the angle segment construction theorem. I'm not sure anyone else does. Theorem 39 says, let angle ABC be an angle and EF a ray on the edge of a half plane H. There exists a unique point D in H such that two things happen, such that the angle DEF is congruent to the angle ABC, and the segment ED is congruent to the segment BA. So the previous construction postulates and theorems that we had in this section with angles only specified that there was a unique ray or a unique angle that made something happen. But this is saying that not only is there a unique ray, there's a unique point on that ray which makes this theorem work. So again, the picture of what's going on is helpful. So let's say we've got this. We've got the point A, B, C. We've got an angle like this. And then we've got some ray E, F, and some half plane H specified. We'll make it the right-hand side again. And this is saying that there's a point D out here, there's a unique point D out here that makes two things happen simultaneously. The first is that we want this angle, DEF, oh, I should write down that, to be congruent to the angle ABC. So we want those two angles to be the same. But then we also want the segment ED to be congruent to the segment AB. We want both those things to happen at the same time. Turns out that we want to do this often enough that we don't want to cite two theorems over and over again. It's going to be much more efficient for us to just create the angle segment construction theorem and use it when we need to. And the proof really is just combining those two facts together. So by the angle construction theorem, we have that there exists a unique angle, I'll call it GEF, with G in H and angle GEF congruent to angle ABC. So this G might be somewhere out here. The angle construction theorem doesn't give us any control over the point G that's used to define the other side of the angle with EF. But now, by the segment construction theorem, there is a unique point D in the ray EG such that the segment DE is congruent to the segment AB, or I think I've got that backwards from how I wrote it down before, yes, such that the segment ED is congruent to the segment BA. Now we're almost done, but let's go back and make sure. We want to make sure that this point D that we have written satisfies all the conditions that it has to satisfy in the conclusion of the theorem. So we definitely have that the segment ED is congruent to the segment BA. That was the last thing we needed up here. Now, we have that since D belongs to EG, we have that angle DEF is equal to angle GEF, and angle GEF is congruent to angle ABC, so angle DEF is congruent to angle ABC. So we have that angle DEF is congruent to angle ABC. That didn't require too much work, just noting that by choosing a different point on the ray EG, we don't change the angle at all that we're defining. Now there's one more condition on D. We needed D to belong to H. And so we should make some sort of argument for why that happens. We already know that G belongs to H. That was by the angle construction theorem. So we need some reason why D belongs to H also. But that's theorem 24 from last time, where if you've got some ray that lies where the vertex lies on a line, then all elements of that ray other than the vertex lie in the same half plane. By theorem 24, since D lies in the ray EG and is not equal to E, and G is in H, D belongs to H also. And so that shows that D satisfies the third condition of the point that we want for the angle segment construction theorem, and so we're done. So this winds up being useful to us when we go on to construct more complex figures, which we're going to start doing in the next section, where we start talking about congruence of triangles. Finally, we have theorems on angle addition and subtraction. Again, very similar to our theorems for segment addition and subtraction. So let's look at theorem 40. Let's suppose that a point D is in the interior of angle ABC, and a point D prime is in the interior of an angle A prime, B prime, C prime. And we've got two statements here. We have angle addition, which says that if angle ABD is congruent to angle A prime, B prime, D prime, and angle DBC is congruent to angle D prime, B prime, C prime, then angle ABC is congruent to angle A prime, B prime, C prime. Let's look at the picture. We've got A, B, C, and then A prime, B prime, C prime, and then we're told that D lies in the interior of the first angle d prime in the interior of the second angle. And of course, when we do that, that allows us to construct these angles here. Now, you'll notice that this setup is similar to one of our axioms. In fact, axiom A4, which was called the angle addition postulate, so that's definitely going to be used here. So let's look at what this angle addition statement says. So let's assume that angle ABD is congruent to angle A prime B prime D prime, and angle DBC is congruent to angle D prime B prime C prime, and the conclusion is supposed to be that angle ABC, the big angle here, is congruent to angle A prime B prime C prime. Rather than go through a proof of this, let's just look at how it would go really briefly. So, first of all, since angle ABD is congruent to angle A prime B prime D prime, that means they have the same measure. That's the only thing it means. That's what congruence of angles means. So that means that there's some number, whatever number is the measure of angle ABD, we'll call it x, is also the measure of angle A prime B prime D prime. Similarly, the measure of angle DBC and the measure of angle D prime B prime C prime are the same. Well, now, by axiom M4, the angle addition postulate, we have that since D belongs to the interior of ABC, we have that the measure of angle ABC is equal to the sum of the measures inside. So the yellow angle is x plus y on the left. But exactly the same statement holds over on the right here. So we have that the angle A prime B prime C prime has a measure that's equal to the sum of the measures of the angles A prime B prime D prime and D prime B prime C prime. So that's what angle addition says. It's basically just showing that the measures of the two big angles are the same because they can each be expressed as a sum of the measures of two smaller angles, and the hypotheses of the theorem say that, well, those smaller angles have equal measure. And then we also have angle subtraction, which is similar but goes the other way. It says that if angle ABD is congruent to angle A prime B prime D prime, and angle ABC now is congruent to angle A prime B prime C prime, then angle DBC is congruent to angle D prime B prime C prime. So let me adjust the figure that I had before to see how that's going to go. So in this case, we still know that the angle ABD and the angle A prime B prime D prime are congruent, therefore they have the same measure. But for angle subtraction, we have that the angle ABC is congruent to the angle A prime B prime C prime, so those two are the same. Well, by the angle addition postulate again, we know that Z, the yellow angle in each case, has to have a measure that's equal to the sum of the red angle and the blue angle. Rearranging that fact, we have that the blue angle on the left has to be Z minus X, has to be the measure of the big angle minus the measure of the smaller angle inside. But of course, the same thing happens over in the right figure as well. So again, we see that the two angles that we cared about, the blue angles, are equal in measure, and therefore they are congruent. All right, couple more couple more things to look at. One definition that winds up being very important to us. So let's look at definition 41. Suppose that we've got 5 points. B, A, C prime. We have B prime, A, C, and the line BC is not the same as the line B prime. BC prime is not equal to the line B prime C. The angles, angle BAC and B prime AC prime, are called vertical angles. And we say they form a vertical pair. So let's look at the picture of what's going on here. We have a couple of lines, and we're told that we have that A, first of all, A is going to lie on both of these lines. And we have that A lies between B and C prime. And then we also have that A lies between B prime and C. And then we're told that these two lines are not the same, that the line containing B and C prime is not the same as the line containing B prime and C. Now, the two angles, BAC and B prime AC prime, are called vertical angles. And these vertical angles are very important to understand the relationships between. Now, this is something that you may very likely have encountered in previous geometry courses, and the big fact about vertical angles is that they're always congruent. So theorem 42 says that vertical angles are congruent. So the proof for this, which I won't write out in full detail, compares the two angles that we care about, BAC and B prime AC, to another angle that basically sits between them. Notice that the angle CAC prime forms a linear pair with both of the green angles, or with each of the green angles, I should say. So we have that angle BAC and angle CAC prime form a linear pair. So the measure of angle BAC plus the measure of angle CAC prime equals 180. Also, the same thing is true for angle B prime AC prime. That's also an angle which forms a linear pair with the angle CAC prime. So we get this relationship here. But that means that the measure of angle BAC is 180 minus the measure of angle CAC prime, but that's also exactly what the measure of angle B prime AC prime is. So that means that angle BAC is congruent to angle B prime AC prime. So it's a very straightforward argument, just using our facts about linear pairs and how their measures compare to one another. But it's very powerful. It's a very powerful theorem in terms of what it allows us to prove moving on. All right, let's look at theorem 43, which says that if two lines intersect and their union contains a right angle, then it contains 4 right angles. So let's sketch out what this sort of situation would be. So we want to take a couple of lines that intersect at a point here, and our hypothesis is that their intersection contains at least one right angle, that there's a right angle that's contained in the union of these two lines. And the statement of the proof says that, well, then, or the statement of the theorem says that, well, then it's going to contain 3 other right angles. So let's go ahead and do this, and let's be a little careful and see how we want to take this statement, which doesn't involve any point names or anything like that, and very carefully write down what we would want this to look like. So proof. Let's let L1 and L2 be lines intersecting at a point A. So when two lines intersect, usually you'll want to give it, you'll give that point a name, because that point is usually going to be very relevant. Now, by the hypothesis, the union of these two lines contains a right angle. Therefore, we should be able to find a right angle in there. So by the hypothesis, there exists a point B in L1 and C in L2 such that angle BAC is a right angle. So we've got some point on one of the lines and some point on another one of the lines such that the angle BAC is a right angle. Now, I've drawn here my picture with the right angle towards the upper right of the page. And of course, we don't know that ahead of time, but there also wasn't anything else specified about my figure. And so if the right angle happened to be somewhere else, we could just rotate the whole thing. And we haven't messed with it much. However, now that we've given these things labels, we want to make sure to keep them straight. So the point B has to lie on the line L1. That's what we said. The point C lies on the line L2. That's also what we said. And A is their intersection. And we're told that the angle BAC is a right angle. And we're going to try to show that there are 3 other right angles here, which means we need some way of describing these other angles in the union of these lines, which means we need points to describe them. If I want to talk about this angle down here, well, that involves the ray AC, but it also involves the ray on L1, which is opposite of B. And I don't have a name for that yet, so I need to give it. I need to give myself one. So let B prime be in L1 such that B a B prime. So I just want to take some point down here on the other side of L1, and this is the way that I do it. I say let B prime, a new symbol, I can't use a symbol that I already have, be a point that satisfies this relationship B a B prime. Now we know we can do this because this was one of the facts that we proved about betweenness. Given a line and given 2 points there, you can always find points that lie on either side of those two or in between them. And also, we want to let C prime be in L2 such that C prime AC. So now we have symbols that we can use to talk about all the other angles. So let's do that. Now, we can attack them a couple different ways, but let's do it this way. Angle C prime AB is congruent to angle BAC since they are a vertical pair. This is using Theorem 42. So we also know by Theorem 35 that any angle congruent to a right angle is a right angle. So by Theorem 35, angle C prime AB prime is a right angle. Okay, so that gives us one of them. So let's look at, let's say, CAB prime, the lower right angle here. Now, what we see is that this angle forms a linear pair with a right angle. Now, we haven't actually proven something that explicitly says that if an angle forms a linear pair with a right angle, then it itself is a right angle. Now, that happens to be true, but we haven't written it down yet. So we either need to use some other argument, such as the argument you would use to prove that result, or we need to prove that result separately and then apply it here. So one way that I might approach this is the following. Let me go to a new page, prove a lemma, and then come back. So let me prove the following lemma. The term lemma is usually used to describe results that on their own aren't usually used as the conclusion of some big argument, but their lemma are usually used to describe proof techniques or little ways that you can get from one step to the next in a proof efficiently. Essentially, they summarize a common proof argument, or a common argument found in a proof into just a single citation you can use, rather than having to write that statement or that argument out every single time. So let's call this lemma A. And lemma A says that if angle ABC and angle DEF form a linear pair and angle ABC is a right angle, then angle DEF is a right angle. So the proof is not difficult. So since angle ABC is a right angle, the measure of angle ABC is equal to 90. Since angle DEF and angle ABC form a linear pair, the measure of angle DEF plus the measure of angle ABC equals 180. Therefore, the measure of angle DEF is equal to the measure of angle ABC, is equal to 180 minus the measure of angle ABC, which is 180 minus 90, which is 90. And now, by Theorem 35, angle DEF is a right angle. So we showed that angle DEF has to have angle measure 90. By Theorem 35, that's enough to show that it is a right angle. I strongly encourage you to get in the habit of proving a lemma like this, you'll often find that a proof is easier to follow if you break it up into little chunks. And especially if those little things that you prove along the way could conceivably be used in other proofs, it's very useful to write them out separately. So on homework problems, for instance, you may find it helpful to prove one or two lemmas before actually going to prove the main statement that the question asks you for. And a lot of times what you'll find is that the proof is easier to read and easier to understand and often easier to write when you break it up into discrete chunks like that. So now that we've got this lemma A, we can finish off the previous theorem very quickly. By lemma A, angle CAB prime is a right angle, since it forms a linear pair with angle BAC. Similarly, angle BAC prime is a right angle. And now we're done, because we've shown that that we have four right angles, BAC, which we started with, BAC prime, CAB prime, and B prime AC prime. Now, what you may notice here is that, well, now that we have the lemma, couldn't we have used that to get the angle B prime AC prime without even going through the vertical angle argument? And the answer is yes. And if I were writing down this theorem again, I very well might want to just say, oh, okay, I see a more efficient way of doing that. Let me just get rid of that middle part of the proof where I'm looking at B prime AC prime, and let me use lemma A and say that, well, going from BAC, I can prove that B prime AC is a right angle because they form a linear pair. And now that I know that B prime AC is a right angle, I could get that this angle, B prime AC prime, is a right angle because it forms a linear pair with B prime AC. And then I could maybe even continue around and prove that BAC prime is a right angle by showing that by observing that it's a linear pair with B prime AC. That would probably be a more efficient way of writing down the proof. Another thing to remember when writing proofs is that your first draft does not have to be the one that you finish with. Professional mathematicians, when they sit down to write a proof, the first goal is to get a correct proof, is to get a proof that actually shows the thing that you want to prove. But you don't stop there. You don't stop when you just have a proof. You continue looking for ways of making the argument more straightforward, more clear, and easier to understand. This is for two reasons. First of all, mathematics is about communication. You are communicating a line of reasoning to someone else. And the more efficient and simpler you can make that line of reasoning, the easier it's going to be for the other person to understand it, and the better a communication it will be. Second, the simpler your argument is, the less likely you are to have made a mistake. Everyone's human. The possibility for error exists. And by making your proof as simple as possible, as straightforward as possible, you are more likely to catch any errors that may exist. So when proving a result, there are three things that you want to look for. I call them the 3 C's of proof writing. And in order, they are that you want your proof to be correct. That's absolutely essential. If your proof isn't correct, then it's useless. Once your proof is correct, then you want to make sure that your proof is clear. You want to make your proof as easy to follow as possible. If you have convoluted arguments, that makes it harder to understand. And sometimes there's no way of getting away from that. There are proofs in mathematics that take thousands of pages to prove, that are very difficult to follow. But as much as possible, you should make your line of reasoning clear, explain what you need to, and make sure that whenever you're using a theorem in order to get from one step to the next, that you tell the reader what theorem that is. And then finally, if you've got a correct proof and a clear proof, the final thing that you look for is to be concise. If you can be concise and have a short proof, that is going to be much better than a longer one. And this plays into it being clear also. So a perfect proof will be correct, clear, and concise. And so you should, when editing your proofs, go through them in that order. Your first step, get a correct proof. If you don't have that, you have nothing. After that, go through again and see, all right, can I write this in a different way to make it clearer? And then once you've got it as clear as you can, then you can start asking, all right, can I make this shorter? Do I have redundant arguments in your proof, like I do here? The proof of Theorem 43 here has redundant parts because I use one argument using vertical angles to get one of my right angles to exist, but then I use a different argument to get that a couple of the others exist. But that second argument could be used for the whole thing. So if you can use just one argument to solve your whole problem, use that rather than using two. So those are some general principles for proofwriting that will help you as you develop your style. All right, the last theorem for today is, sorry, not sure what happened. Oh, what happened there? All right, let's look at Theorem 43.